Okay, so you really need to know the derivatives of your trig functions. You need to be able to recognize the derivatives of the inverse trig functions as well. Again, the dx or the dy is a marker. They're telling us what we are anti-differentiating with respect to. And as we do more and more of these, I think they will get a little bit easier. Okay, as one of my college professors said, they're kind of like a little mathematical puzzle. So, do you like puzzles? I like puzzles. All right. Well, what a party pooper. Okay. So let's look for just a second. If we have the integral of the sine of 3x, I'm going to take the antiderivative of sine of 3x, which gives me negative cosine of 3x. Oh, sorry, it's not the x, it's. However, this is not the correct answer, okay, yet. And here's why. If I take the derivative of this, look up here for a second. If I take the derivative of this, the derivative of negative cosine of 3x is sine of 3x, but then I've got to multiply by the derivative of what's inside the parentheses. So there would be another 3 here, okay? And so in order to cancel out that 3, I need a 1/3 out front. So here's a general formula for antiderivatives with trig functions. We use sine as an example, but true for all. If my derivative is something times sine of something x, so the antiderivative is going to be negative cosine of whatever that is divided by whatever the coefficient is of what's inside. So let me do an example there, and I think it will be clear. It says find the general antiderivatives of the following functions, okay? So the antiderivative of secant squared of 3x is tangent of 3x plus c. And then I need to take what's inside the parentheses here, looking at the coefficient, which is my k in my formula. So I take the 3 and I divide it into what's in front here. 3 divided by 3 gives me 1. And so this is my final answer. And I can check it by taking the derivative. Derivative of tangent of 3x is secant squared of 3x. And then I multiply by the derivative of what's inside the parentheses, which is 3. So let's do another one here. I have the antiderivative of 4 cosine of x. I can move the 4 out since it's constant. So I just have the integral of cosine of x, which is sine of x. But on this one, I'm going to need to divide by the coefficient again, okay? So I've got sine of 4x plus my constant there. But then because I have a 4 here, I'm going to take this coefficient and divide it by what's in front of the cosine, which in this case is 1. So I need a negative 1/4 sine of 4x. So one more here. I have the integral of 4 cosecant of 4x cotangent of 4x. The antiderivative of cosecant 4x cotangent 4x is, it's what? Negative cosecant of 4x plus c. And now I take the 4 and divide it by what's in front, which just gives me 1. So this right here is my final answer. So that is for trig functions. If you have polynomials or exponents, we've seen this, but let me go back over the rules. The antiderivative of x squared, I add 1 to my exponent, and then I divide into the coefficient with the new exponent. So this would be 1 divided by 3 plus c. And so on the next one, I add 1 to my exponent. So 2/3 plus 1 gives me 5/3. And then I divide, which gives me 3/5. And again, I need a plus c. So here's the general formula. If I have ax to the n, I'm going to add 1 to the exponent. So that would be n plus 1. And then I'm going to divide that new exponent into the coefficient. So I've got an a over n plus 1 out front here. And then I add on the plus c. So let's look at a few of these examples. It says find the general antiderivatives of the following functions. So I have the integral of 5x cubed dx. So I add 1 to the exponent, which gives me x to the 4th. And then I'm going to divide the new exponent into my coefficient. So that gives me 5/4. I add a plus c on there, and you could check it, right, by taking the derivative. 4 times 5/4 gives me 5, and then I subtract 1, which gives me x to the 3rd, so it's good. How can I rewrite this one? I'm going to have 5x to the -3, and I need a dx. So I add 1 to my exponent, which gives me x to the -2. And now I'm going to divide. So I've got 5 divided by -2, so -5/2. And then I need my plus c. Okay, well, how do I rewrite this one? That's going to give me the integral of 4/3 x raised to the 1/3, and then I need my dx. So I add 1 to the exponent. 1/3 plus 1 gives me x to the 4/3. Now I divide. So 4/3 divided by 4/3 gives me 1. And I add on my plus c. And the last one here, how can I rewrite this? I've got the integral of 2 minus, and let's pull that 1/4 out. So I've got 1/4 x to the -2, and then I need a dx. Okay, so the antiderivative of 2 is 2x. Again, how do you know it's an x and not a y? Because of my dx here. It tells me what I'm integrating with respect to. Here, I'm going to add 1. So -2 plus 1 gives me -1. And then I'm going to take the -1 and divide. So -1/4 divided by -1 gives me positive 1/4. Any questions on that one or those for me? Okay, let's look at one last thing here. We have the fundamental theorem of calculus, part 2, which we saw before the break, and it's kind of important. Okay, it says if little f is continuous on an interval from a to b, and big F is any antiderivative of little f on that interval, then we have the integral from a to b of little f of x dx. And it said that the antiderivative of little f is big F. But then we have bounds. And so notice on all the ones that we've done before, we did not have bounds. And if you do not have bounds, you've got to put the plus C. However, here, if we do have bounds, following the fundamental theorem, and we saw a couple of these examples yesterday on your review, I'm going to plug the bounds in. So I got big F of B, and then we subtract minus big F of A. So example 3 here says to evaluate the integral. I have the integral from 0 to 16 of x to the 1/4 dx. And let's think just for a second, okay? What am I finding here? Again, whenever I integrate, it's the what? It is the antiderivative, but I'm finding, think about our review yesterday. What were we finding with those integrals? It was the area under the curve. So in this case, I'm finding the area under the curve of the function x raised to the 1/4 from 0 to 16. So I'm getting a specific numerical answer, okay? As opposed to what we were doing previously when we were doing just general antiderivatives and we had the plus C. But here I'm going to have a specific numerical answer. Okay, so I add 1 to my exponent, which gives me x to the 5/4. And then I need to divide. So I flip the fraction. So I have 5/4 x to the, 4/5 x to the 5/4. And now I'm evaluating from 0 to 16. So I'm going to plug in 16. And so now let's say, hypothetically speaking, that this is like a multiple choice problem and we can't leave our answer here unsimplified and we're in the calculus jungle without a calculator. How would we work this out? So you are saying, hold on, we have 4/5. You were saying we could write this as 16 to the 1/4 raised to the 5th power. If I raise a power to a power, I multiply, right? So this is 1/4 times 5. That's the same thing. And I could write this as 4/5 times the 4th root of 16 raised to the 5th. What's the 4th root of 16? 2. So this is 4/5 times 2 to the 5th. And what's 2 to the 5th? 32. So this is 4/5 times 32. Now it's like 4th grade math, right? Let me see. 4 times 32. 128/5.
Would the answer be wrong if we didn't draw that? We just left it as 4/5, 16.
The answer to that is it depends. Okay. If I ask for a singular numerical answer, then yes, you would lose some credit. Or if it's multiple choice, that might be the final multiple choice answer. So you would have to. Okay. If it's just a free response question and you're not asked to do that, then leave it right there. Okay. Well,